Okay, off we go. So let's see. Yeah, new section today. 5-3. This is the fastest section in the book. There's hardly anything that happens in this section. Make sure to give it a read, right? But there's really very little that I feel necessary to actually say about this. So whoa, I hit the wrong button again. I'm going to kind of show you an example of the big idea, and I think everything else is pretty similar, frankly. So the big question is how to switch the order of the differentials. So if we have an integral like this, for example, what would happen if, okay, I'd like to do that dy dx instead of dx dy. And we know we can't just switch the bounds. That doesn't make any sense anyway. So how do we do that? And the short version of the answer, there we go, is that it's sort of a two-step process. Step one is to reverse engineer what is the domain. What is the actual domain for the double integral that this iterated integral represents? And once you know what that domain is, it's all over but the shouting, because, of course, we already know how to turn a domain for a double integral into bounds for an iterated integral. So basically, you reverse engineer the domain and then just slice it up with the differentials in your preferred order. That's kind of all there is to it. So now, how do we do that first step? How do we figure out what the domain is? Again, I think an example should be sufficient. So let's look at what we have here. These bounds, what is that actually telling us? Well, let's look at the outside bounds. Right, we've got y going between 0 and 1. All right, well, here's y equals 0, here's y equals 1. So our domain must be inside of that. After all, the y slicing process consists of just slicing up between 0 and 1. Does that make sense to everybody? Okay. All right, now, from where to where between y equals 0 and y equals 1? Well, it kind of tells us right here that the lower bound is going to be, for whichever y you might happen to be looking at, between 0 and 1, the lower bound for x is going to be y. Said differently, the lower bound will always be on this curve, x equals y, and that curve is easy to draw. And likewise, the upper bound for x says right there is 1. That means that the upper bound for x on any y slice is on that curve, which is easy to draw. And so that's the process, pretty much. So whatever these bounds are, tell you what your domain is. And as we just discussed a second ago, once you know what your domain is, then it's just a matter of doing the usual slicing process to slice that up and infer your new bounds. How are we doing? Is everybody buying it? All right, that's pretty much the whole section. Now, let me address the question, why would you ever want to do such a thing? I'll say a quick word about this. Let's look at this original integral. I mean, who needs to switch the bounds anyway? Why don't we just compute this as is? And the problem comes from the very inside, so the first actual integral we would have to compute is this right here in green. Now, how do we compute this integral? Well, we have to find an antiderivative of e to the x squared. And you can't. Not without using power series, as it turns out. Proving that you can't is beyond what we can do in this course, but it remains true that you can't. And if you don't believe me, give it a try. And get ready to fail. Okay, so that makes this a pretty undesirable phrasing. And then if we have a means instead of doing it the other way, now let's look at the inside integral here. Now again, we find ourselves in this seemingly undesirable position of having e to the x squared as our integrand, but very critically, now y is our variable, which means, in fact, this e to the x squared is just a great big constant, and anti-differentiating a constant is very straightforward. And then you plug in the bounds, 0 to x, blah, blah, and it's all over. And notice that the resulting single variable integral is not the impossible x integral that we were looking at originally. Now there's an extra factor of x. You can just do a u substitution, let u equals x squared. Everything falls apart, falls into place. So weirdly, sometimes changing the order of integration makes a problem computationally much easier. Okay. All right. So that's 5.3. Moving along to 5.4. 5.4 is triple integral. Oh, I'm sorry. Question. Yeah. Yeah, this is a fancy way of saying without power series. So in other words, if you wanted to write the antiderivative here that we're referring to, in terms of exponentials and logs and polynomials and stuff like that, so you would have to write it instead as an infinite power series. Yeah. Okay. Yeah. So triple integrals. Here's the broad stroke of triple integrals. It's just like double integrals, just a little bit more so. Right? It's 3 instead of 2. It's shockingly similar. Now, in terms of the human experience, the human experience is going to be a little harder because we are three-dimensional critters. Our imagination is really pretty limited to 3 dimensions. You can debate about maybe with some great effort you might be able to visualize 4 dimensions in some sense. Very little with great effort. And it's not something that at all expected in this class, to be sure. We're going to have to find different ways of thinking about things, but in terms of the mechanics and in terms of a lot of the interpretations, it's just like double integrals. So just to remind you, here's when we introduced the idea of a double integral, and I made the observation that single variable integrals, namely the idea of taking an interval, chopping it up into little pieces, and making the usual chop it up, add it up argument, right? Gives us our regular Riemann sum, our single variable Riemann sum. And a double integral just says, well, we're going to have now a 2-dimensional domain. And again, well, we're going to do pretty much the same thing. We're going to chop it up into little pieces. Right? It's harder than it looks. Chop it up into little pieces. And again, we're going to make a chop it up, add it up argument. I'm going to say, well, instead of looking at little sub-intervals, answering the question on the sub-intervals and then adding up over all of them, here, I'm going to look at whatever the question is, whatever we might happen to be computing, be it mass or population, whatever. I'm going to look at it on little sub-rectangles. I'm going to answer the question individually on each sub-rectangle, stuff per unit area times area, whatever that stuff is. And then add up over all these rectangles. And yeah, there's more rectangles than there were intervals. And yeah, there's different details. Don't get lost in those details. The big picture is chop it up, add it up. Right? Specifically, we chop up the domain. Okay, so now we're just going to entertain the question of what if we really have to do kind of that same thing, but our domain and what we need to chop up is now not an interval, not a rectangle, but a 3-dimensional solid rectangular box. Maybe I want to compute the amount of mass in this 3-dimensional box. For example, maybe I know density is a function of positions, something like that. Well, again, now there's a bunch of details, and it's easy to get lost in the details and to, worry about, what do we mean by all of this stuff, and what's K, and there's lots of other little micro minutia that have to be written down, of course, to make this all precise. But big picture, chop it up, add it up, right? Where it's hard for me to draw three-dimensional slices, but you could imagine if I were to take a knife and cut this up in all three different directions, I would get not sub-intervals, not sub-rectangles, but what I will call sub-boxes. On each box, I can talk about whatever it is that I'm computing, whatever that stuff is, let's say mass, because it's relatable. On that little tiny little sub box, mass is mass per unit volume times volume. Right? So it's volume instead of area, instead of length. It's mass per unit volume instead of mass per unit area, instead of mass per unit length. Right? The same basic idea, just three-dimensional instead of two. And then again, now I have to add up, and instead of adding up over an interval, instead of adding up over a rectangle, now we're going to add up over all of this. We're going to add up all of those terms in three different directions to get the final total answer. So it's just like a double integral, just more so. Just three-dimensional instead of two. Is everybody on board? Everybody kind of see the pattern? Now, by the way, how, pray tell, are we going to add up in three different directions? That sounds scary. Do you notice we never really quite did that with double integrals? With double integrals, pretty early on, we made this, we made this observation that because you can compute you can compute volume under a graph with both double integrals and iterated integrals. The big observation then was that I don't even really need the concept of volume. I can compute double integrals with iterated integrals. We have to write down that two-index summation. We never actually have to punch it up, right? I mean, we never have to actually compute that. And so something very similar is going to happen over here. So, don't worry about the actual adding up in three directions. Okay. So real quick, now this is largely just repeating what the initial motivation was, but let's take this idea. Suppose I have this rectangular box, three-dimensional rectangular box, and there's some sort of, gravel maybe, some sort of stuff in the box, and I know how density varies with position, right? So, and notice it's a function of all three variables, so I can't just sort of take, like a Calc 1 take on a question like this would be to look at one thin slice at a time and try to hope that maybe the density is a constant on that whole slice. It's not, in this case. But we can take a triple integral approach and say, look, mass is an accumulating quantity, the whole of the sum of the parts. Notice I'm using this integral shorthand. Right? That's actually just shorthand for a Riemann sum. Whole is the sum of the parts, and on any given piece, mass is mass per unit volume times volume. So just like we did for double integrals, except it's volume instead of area. All right. Is everybody happy with that? Okay. Now, how to compute. We will get to. Before we get to the turning the crank and the actual computations, I do want to warn you, I think this is a really important warning in terms of how to think about it. And this is where we have been. We've talked about single variable integrals, we've talked about double integrals, and we've talked about different kinds of applications. So, for example, when you're looking at you're looking at a single variable integral, I'm going to call that a one-dimensional integral because you have a one-dimensional domain. Whatever application you might be looking at, you got a one-dimensional domain. And the way we tend to visualize this is with graphs. That's the first picture that everybody draws, and the big idea is that the integrand itself is kind of represented by sort of height there. And so the punchline is that even though this is a one-dimensional integral with a one-dimensional domain, we are going to look at a two-dimensional picture. And again, that's every single variable calculus course I've ever heard of does it this way, and frankly, as they must. What are they going to do? Not draw that picture? That'd be crazy. Okay. And then in that context, you talk about examples like this and where's the area? Students kind of want to see that there's an area. Students get real attached to this graph point of view, and y'all heard me say it a million times, you don't want to be too attached to the graph point of view in a multivariable context. So I want to encourage you to think about things this way. We have a one-dimensional integral defined on a one-dimensional interval on the one-dimensional x-axis, and that's exactly the picture that we're looking at in an example like this. If you want to compute the mass on this rod, mass per unit length, then okay, here's the thing that you're looking at. And sure, I can't see the integrand, so I don't have really much of a comebacker for that. Yeah, the graph picture is nice in the sense that you can see the integrand. Okay, nevertheless, this point of view over here is a one-dimensional picture for a one-dimensional integral. Now, y'all can see this coming when you have a double integral with a two-dimensional domain. Well, you can view that two-dimensional domain in relation to the graph picture, and the graph picture over here is now three-dimensional. Okay. Or you can view just the two-dimensional domain itself, right? And this would be the picture if you have a mass distributed across an area, and then of course, obviously, two-dimensional picture of a two-dimensional scenario. And this one's starting to have a little bit of merit to it at this point. I mean, you look at the graph option here. It's hard to draw these three-dimensional pictures. The graphs are in three dimensions. Our paper is two-dimensional. The things we're drawing themselves are two-dimensional surfaces. Our pens are one-dimensional. They make one-dimensional curves. Right? It's not the match made in heaven that this was. So this is a lot less appealing. And all of a sudden, then the lower dimensional advantage of looking at things this way starts to see the merits. All right. So, well, here's the thing. Pattern continues. If you were to try to visualize triple integrals in terms of graphs, you would have a four-dimensional picture, and I don't think you could do that. I certainly can't. Right? Whereas, on the other hand, if you want to understand, you have a three-dimensional domain, and you want to understand that in the context of, the question of computing mass. Okay, yeah, cool. We have a three-dimensional domain. There's a three-dimensional picture of my three-dimensional domain. Three-dimensional picture, and okay, sure, it's a little harder than a two-dimensional picture, but it's possible. It's on the table, as opposed to the graph picture, which is out of the question, non-starter. Everybody okay? So, in anticipation of this, that's why one of the reasons I've been pushing this point of view right here. Think about everything in terms of the mass question, or the distribution of stuff metaphor for these integral constructions, because it's dual. Right? It leads to it's a sustainable pattern, at least through three dimensions. Whereas, by contrast, this reaches a dead end, and we lose. Does that make sense? Okay, now here's the last thing I'll say about this, and this is kind of a warning, FYI, and you got a heads up for the following. It is not unheard of for students to say, all right, I choose this picture for single variable integrals, and then this picture for double integrals, and then, lack of options, this picture for triple integrals. I guess I guess you could limp along that way, but then, look, you have some pretty severe disadvantages then. Then the way you're thinking about triple integrals, the two-dimensional analog is not something you've given any consideration to. You don't have that to kind of, be your launching pad. You can't say, I'm going to think of triple integrals just like I did with two-dimensional, double integrals just, one dimension up, because you're not thinking about double integrals this way. Right? Worse, notice both of these pictures are three-dimensional pictures, right? And so I've gotten questions from students many times over the years. How do I know whether a question should, if there's a question that has volume in it, how do I know whether it's a double integral or a triple integral? Well, the point of confusion there is students are conflating these different points of view. Right? So I am not saying that I am opposed entirely to the graph point of view. I'm not saying that at all. Right? What I am suggesting is that you make sure that you are comfortable with all of these points of view right here. Make sure that you're comfortable with the comparison. Make sure you see the pattern. I'm a big believer that if you understand sort of the patterns in related constructions, then it'll all just kind of fall into place. Everything you understand about this will help you to understand this. And then, okay, yes, there are situations where I suppose these have their uses here and there. Oh, that's a bad color choice, wasn't it? These have their moments. Oh my gosh. Got it, okay. These have their moments. And so, if you want to think about those, yeah, sure. I mean, you do have to do that sometime. But I want to encourage you to entertain the idea of transitioning your point of view on integration to not be graph related. It's usually not the right point of view. I want to encourage you to think of all integrals in terms of accumulation of stuff over domains. And math is kind of a nice, familiar, viscerally relatable kind of stuff. That's my favorite metaphor. Is that cool? All right, now that's just advice for your consideration. Let's talk about how to compute them. It's pretty similar. Y'all recognize this diagram. In fact, let me switch back over. Here's the analogous diagram for double integrals. And, of course, what we had here is volume. That's sort of the graph point of view on double integrals. It's three-dimensional. And, okay, well, that means that here, that would be a four-dimensional thing, and we can't do it, right? So we can't use that. I'm not going to be able to argue about this thing that I can compute two different ways, the punchline of which is going to be that these are equal. So I can't give you that argument, but I will say there is a different argument, a heavily algebraic argument that is surprisingly sophisticated. Got to worry about certain aspects of limits. It's really not obvious. It's definitely beyond this course. Take my word for it, though. Those are equal, and it's fine. And so the strategy, again, just like with double integrals, whatever your application is, write it as a triple integral, rewrite it as an iterated integral, punch it up with the fundamental theorem, just like with double integrals. Okay. This example is really analogous to one that we did with double integrals. And I just kind of want to point out, don't forget that there's a bunch of variables running around. You got to keep track of which variables are playing which role. Look at this integral right here. You see z is our variable. Don't forget variables further to the outside. Now I can't draw the picture to justify this conveniently, right? But variables further to the outside you treat as constants. That means that x and y, and of course 2, constants. So when you do the antiderivative here is a simple matter of saying, well, I have constant times z, and that's an easy antiderivative, right? The antiderivative, let's say it this way, the antiderivative of 2z is z squared. Is that cool? Okay. So very important to keep track, at which stage is which variable playing what role. Okay. What do you do with non-rectangular domains? Well, let's go back to the double integral context, and here's the picture we drew for the double integral context. And again, our original picture was in terms of graphs, because again, you did that little bit of satisfaction. And again, unfortunately, I can't draw graphs of functions of three variables. The analog of this picture for triple integrals, we just can't draw. But what does remain is the pattern that we saw when we drew only the domain. And the big idea of the pattern here is, well, we're going to first decide, let's say, that we're going to slice in the y direction. We're going to find the starting and ending values of that variable, C to D in this case. Then we're going to fix some value of that variable. Look on the slice of our domain corresponding just to that variable, just to that value of that variable. And then we're going to say, all right, well, what's the starting and ending values of the next variable? Right, so next variable being x, and look and see what the starting and ending values of that are. And the pattern is going to be the same. It's just 3 variables instead of 2. So 3 iterations instead of 2 iterations. 3-dimensional pictures instead of 2-dimensional pictures. But totally analogous. Okay, so again, here it is. We're going to pick a coordinate axis and do the slices. Identify the first and last. And then fix one of those slices and move on to the next variable. So let's see this in action. It's a lot easier to see this by picture. So here's a picture, generic. Let's not worry about the actual algebra here, right? So the actual, is this an ellipsoid or what is this? Don't worry about the specifics. We got a bunch of examples to follow. All right, well, let's see here. Suppose I do my x slicing on the outside. Let's try to get all this on the screen here. Suppose I do my x slicing first. That means I'm slicing perpendicular to that axis. Slices perpendicular to that axis are planes cutting through our solid, which is going to give me some sort of a cross section. Right? Let's talk about first and last. Well, depends on the shape. Got to look at the picture. By the way, having a good picture is going to be indispensable in doing these kinds of questions. The picture tells you so much, and we'll see examples of that as we go along. But I claim that the very first slice is going to be way back here on the far end. There's going to be some very first slice, and that will give us our x1. And then there's going to be a very last slice on the very near end, and that will give us our x2. Okay, now, having done that, we fix a value of x. We restrict our focus just to this slice. Now, previously, this was this was like a line segment. A slice of an area is a line segment. Here, a slice of a volume is now an area. It's a little flat surface. And we move on, though, to the next variable. Let's think about how to slice this perpendicular to the y-axis. And perpendicular to the y-axis, of course, we're going to have slices like that, and I'm going to make a geometric appeal. If you have this x slice that's perpendicular to the x-axis, it's like a segment of a part of a plane perpendicular to the x-axis. And if you slice that like so, perpendicular to the y-axis, the slice of the slice, let me do it like that. The slice of the slice is going to be a line segment. And again, we just have to think about first and last. Okay, so those line segments, those y slices of our x slice, the first one is going to be at a point like that. Again, details will follow in the examples. That will give us what we're going to call y1. And then there is a last slice, and that's going to give us what we're going to call y2. And notice these y1 and y2 are the bounds for that second integral. Everybody on board so far? Everybody notice it's the same pattern that we did for double integrals, I hope? Just, three-dimensional pictures, and we've got a whole extra dimension that we're going to have to consider now, but it's the same sort of process. Okay, real quick, let me point out that where these first and last points for the y bounds come, notice they depend on x. Well, sure, of course they do. Different values of x will give you different cross-sections. You'll have entirely different cross-sectional areas that will have totally different y bounds. So they're going to depend on x. Okay, and then we fix a value of y. Now keep in mind, fixing that y, this is after we've already fixed the x. So we are now entirely confined to this y slice of our x slice. Just that line segment. Forget about the whole rest of the domain. We're just looking at that slice of our slice. And on that slice of our slice, we now want to know what's the range of values of z as I move along that slice as I move in the z direction. And you can see there's going to be a starting z and there's going to be an ending z. And those are going to be our inside bounds. And that's our iterated integral. Okay. All right, let's do one. Dive in. Examples really help for this kind of stuff. A couple of quickie observations. Just like double integrals, notice we construct the integral outside in. Of course, you have to compute it inside out. Notice the bounds can be functions of the variables further to the outside, just like with double integrals. And then this same pattern, how are we going to figure out what bounds are? Well, we're going to identify the key relevant points. We're going to notice that they are on some specific surfaces that will have certain equations in which I can solve for the bounds that I'm looking for. Same pattern with double integrals. Yes?
So can you also switch up the bounds?
Yeah, you have 6 different options of how to slice. That's right. And so we call this a good news, bad news situation. And it's good news because you've got options, right? Options are good. Well, but the downside is you have to choose between 6 different options. So yeah, there's more to consider. And there's a lot of really important questions in the direction of what you asked of how do you know what is the best way to slice? And I'm going to spend a bunch of time talking about that in a bit. Okay, let's get one under our belts first, though. Here we go. This example here. And like the first example, to keep the geometry pretty easy, keep the algebra pretty easy. The goal here is not to get the answer. The goal here is to focus on the process. Don't think about whether you get whether you can think of the answer in some other way or whatever. Think about the process here, right? So here's our domain. And as we have done previously, we're going to start assuming that we have some double integral for whatever reason. Why? Who knows? Not what we're interested in here. And the question is going to be, how do I turn that into an iterated integral? Okay, so again, outside in. Now, for no particular reason, I'm going to start with x slicing. It goes in that direction. The first slice is here. The last slice is here. Is that cool so far? Okay, now, there are some cases where you're looking, or you're trying to infer what are the corresponding x bounds. There are some cases where, as I like to say, the fish just jump in the boat. Sometimes it's really clear. And I'm going to propose that the lower bound here is pretty. I mean, you could look at that whole first slice. I mean, it's literally in the plane x equals 0. So, of course, that bound is x equals 0. So if you get a freebie, cool. All right. Now that said, let's talk about this last one. Now you could argue that maybe you're real good at the geometry and thinking about the blah blah, and you could figure this one out maybe easily too. But let's think about the process on this one. That's the relevant point. That's the last x slice, and I want to identify what surfaces is that on. So, okay, by the way, I'm going to make heavy use of the picture for this. The picture tells me the point I'm interested in is on that plane, which has that equation. Picture tells me so. Okay. The picture also tells me that it's on this plane with that equation. And the picture also tells me, oh gosh, color choices. I'll use, also tells me that it's on that plane that has that equation. Notice these are planes whose equations were given. Is that cool? Okay, so the point that I'm interested in, the point for which I want to solve for x, has to satisfy all those equations. And so, okay, what I'm going to do is I'm going to look at all these equations together and I'm going to solve for x. And whatever I get is that upper bound. And I think this algebra is pretty straightforward. I solve for x in that little trio of equations and boom, 1. Is that cool? Now again, you could probably do that geometry in some, maybe thinking of it in some different way. Not the point. The point is to think about the process here. There will be other circumstances where you can't do it in your head. You need the process. Is that everybody's with me? Okay. All right. Okay, so moving along. By the way, while I'm at it, let me observe. As we were trying to understand this point, the picture told us that these were the 3 of the 4 given surfaces that we want to consider. The picture also tells me which surfaces are not relevant to the understanding of that upper bound, right? So don't look at that equation x equals 0. That's not part of the algebra, right? When you're trying to find the x coordinate of this upper bound, this surface, aka this equation, doesn't have any connection. Right? And I will note that over the many years I've been teaching I've seen a lot of students who had like a high school multivariable calculus course, and the advice that they got in their high school course was, well, you just kind of look at all the algebra, and the algebra will kind of help you just do it. And if you were to follow that advice with this example, well, I mean, if you were to say, let's look at all this, solve for x, you might think, I don't even have to look at the rest of it because right there it says x equals 0, and that's wrong. Okay, so now we're going to fix a value of x per the process on the previous page. We're going to fix an x slice. We're going to focus now all of our attention on this x slice. Forget the rest of the domain. The rest of the domain comes about for different values of x. We're going to look at this representative x slice. And on this x slice, we now want to do our slicing in the y direction. Okay, so y slices, perpendicular to the y axis. We'll have slices sort of like that. Again, geometric appeal. How does that intersect this? And well, we get slices kind of like that. So again, we have to think about first and last. Again, that first slice, pretty obvious. Y is equal to 0 on that first slice. Again, you get some freebies. Gotta love freebies. Right, so that lower bound is right there in the picture. Clearly y equals 0. And again, where it gets interesting is the upper bound. Now, again, let's play the game. What do I know about that point? And the first, you got to doff the cap appropriately, but the first thing I'm going to say is, look, it's on the X slice that I've already decided I'm focused on. So the X coordinate is known, and my little silly superstition for how to remind myself, if nothing else, that X is known is to just write X equals X, and I know it's basically meaningless, right? But I find that helpful. Okay, now what else do I know about that point? And again, you got to look at the picture. The picture tells all. We can't do this without a picture, realistic, feasibly. Well, that orange point I'm interested in is on that plane, that equation. Thank you, picture. And again, from the picture, I see it is on that plane with that equation. Again, the whole reason I'm interested in this point is that I'm looking for the corresponding y bound. I'm looking for the, let's see, what would be the upper y bound. I want to solve for y in all of this. Okay, and you solve for y, and now your y, you'll notice it ends up being a function of x, and it's allowed to be a function of x because x is further to the outside. X is established. My y bounds are supposed to depend on x. Everybody happy? Okay. Alrighty. And then we move along. Now again, let's see here. I'll do this with blue. Now we're going to consider both x and y fixed. We're going to look at that, you might say, y slice of our x slice. Again, it's just a line segment. And again, we want to know now the range of values of z. So we're going to start there where z is obviously 0. Take your freebies when you get them. And the more interesting question, what's the upper bound? Okay, well, that upper bound, well, I already, no, whoops, wrong color. I know x and y. X and y are established. My z bounds are supposed to depend on x and y, so let's just remind ourselves of that. And then what other surface are we on? And again, the picture tells us that we're also on that face, not one of the others. We're on that face, right? Picture's what tells us. And again, we solve for z, the variable in question. And again, it's allowed to depend on x and y, so that's all fine. And that's our upper bound. Everybody happy with the process? All right, good deal. Okay, bunch more examples. Now, a little bit of advice I'm going to give. You do have, you've got 6 different options to choose from as to how you slice. Strongly advise that you don't make a choice now and just kind of, I'm going to be a dx, dy, dz kind of person, right? Because that really won't work sometimes, right? So you need all of this flexibility, right? And a lot of the same advice from just like with double integrals. Try not to slice through corners and edges. You slice through corners and edges, things change qualitatively, just bad things happen, and you're going to end up with multiple iterated integrals to have to compute, and nobody wants that. Try not to, think about which variable you most conveniently and naturally want to view as being a function of the others, if such a variable presents itself. And if so, put it on the inside, where you will have to solve for it in terms of the others. And if you don't make that choice, then you're going to have to solve for one of the ones you don't want to have to solve for, and bad things again happen. So try not to do that. By the way, I'll point out that doesn't always come up. You look at all this algebra, I don't see any variable that I have a preference for solving for more than the others. So sometimes you don't get any such guidance. Okay. The last little bit of advice I'm going to give on this is better seen with an example. So all this business about projections, I'm going to come through and talk about what all this means after we do this next example. And here it is. Why don't I go full screen? There we go. Here we go. I want to get all this on the screen at the same time. Okay. So here's our region. Like that. It's, all the stuff sort of in here. Reminder, part of the question is to be able to look at what's given and draw the picture correspondingly. Right, so that's a good sort of geometry exercise to think through. If you think, all right, what this thing looks like, and then you look at this plane, z equals 1, which is going to kind of effectively make a sort of a cap on top of that. And then it says right here that we want just the part in the first octant, and that's what gives us our actual domain there, right? So make sure you're comfortable with that kind of, there's a lot of geometry. There's a lot, unavoidably, is geometry. Whenever there's a lot of geometry, the ability to draw reasonable figures becomes useful, just unavoidably useful. Right? So let me take this moment to pitch again. If you are maybe not as good as you wish you were at making three-dimensional drawings, which is a lot of students, everything that I have ever figured out about three-dimensional drawing, I've put into some videos. They're in the Miscellaneous Topics playlist on my YouTube channel. Drawing 1 and Drawing 2 are the names of the videos. It adds up to like a little over an hour of discussion, but it's everything that I know about three-dimensional drawing. And in particular, after I list all of the sort of little tricks, I go through a detailed discussion of exactly this figure. And how did I draw this figure? And I'm not gonna brag or anything, but I would call that figure plenty good enough for our purposes. Right? And it's non-trivial to make a plenty good enough figure. Is that yeah?
So, for the process of, drawing this and, visualizing it, would you say that you start with the 2D, and then if you, pick, if you happen to pick Z as your, the one that's, a function of both, would you, drop it down and then create, a 2D picture to figure out the rest? That's
going to be very importantly part of how I slice up this thing, yeah. In terms of how I draw it in the first place, that wasn't how I was thinking about it. Maybe if that's useful for you, then that could be cool too. But it definitely is going to be very important in how we're going to do the slicing. Yeah, yeah, absolutely. Yeah, sure. And there's a lot to say about how to draw the figure, and it's over an hour of discussion. Yeah. Okay, all right. So here we go. Looking at this algebra. Do I want to solve for x? Square roots. All else being equal, if I can avoid it, I'd prefer not to have to solve for x. And all else being equal, I'd prefer not to have to solve for y. So I tell you what, I think it's best to view z as a function of x and y. And as a result of that, I want to put dz on the inside. Anybody see that motivation? Okay. Now, should the outside be dx dy or dy dx? Hard to tell. Turns out in this case it won't really matter much. So I'm going to say let's not worry about that for this example. And I've made an arbitrary choice here, dx dy. Okay. All right. Now, for your consideration, I'm going to propose that we think about, since we've designated x and y as our outside two variables, let's, guided by that, and you'll see why this works out so well in just a moment, let's think about what the projection looks like into, let me try to be better with my drawing. Let's look at the projection into the xy plane. Got our whole solid. I'm going to look at the what you might call shadow down here in the XY plane. Now, why? Well, again, the good news is coming, right? But I claim that's going to be the connection. Whatever the outside two variables are, think about what the shadow looks like in that coordinate plane. All right. Now, with that in mind, that's what that shadow looks like, of course. Okay. Let's start doing our slicing. I'm supposed to start with my Y slicing, and there's the Y-axis, and my Y slices look kind of like this. And you can see it first and last. And now here's my cool observation. Okay, those are what the Y slices of my solid look like. But here's what the Y slices of the projection look like. And notice, they have the exact same Y coordinates. The starting value of Y on the solid is the exact same as the starting value of Y on the shadow. Now, did we just get lucky, or is this obvious? And I think this should be actually expected, because what is the shadow after all? The shadow is just what you get when you look at all the points in the solid. You kind of ignore the Z. You just kind of throw away the Z. Which means you're not changing the X and Y coordinates at all. When you project down into the XY plane, you're not changing X and Y. And if you're not changing X and Y, then you're not changing what the smallest and the greatest X and Y are. All right, so I think that's a cool observation. Now let's take it the next step. The next step would be to, pick a slice. And let's think about the range of values now of X. So as I go in the X direction, and well, here's what my X slices look like on the solid, and here's what the range of values of X looks like on the shadow. And again, it's the same. Well, of course it's the same. They have all the same X and Y coordinates. Whether I attach some irrelevant Z's or don't attach some irrelevant Z's doesn't change what the X's and the Y's do. So the big punchline in it, I think this is a huge one, really valuable computational tool. Whatever your outside two variables are, look at the projection into that coordinate plane of your solid and determine all of these bounds, not by looking at the solid, but just by looking at stuff that happens in the shadow. You can ignore the very difficult to draw three-dimensional picture and just look at the much easier to draw two-dimensional picture. Everybody buy it? Now, that only gives you those first, the outside and the middle, if you will, bounds. Now, what do we do about the Z bounds? Okay, well, all right, so we are going to have to go up to the three-dimensional picture here, and so I'm going to have to look at, for example, a point like that represents certain values of X and Y, and then I am going to have to say, all right, well, there's that corresponding slice, and, Z, the lower bound for Z is, it's going to come from this surface, which, by the way, has this equation. And how do I solve for Z in that equation? Well, it's X squared plus Y squared. And then the upper bound, okay, how am I going to find the upper bound? Well, this point determines the upper bound. How do I solve for Z on that point? Well, it's always conveniently on that surface, which has this equation, which I can solve for Z very easily. And it's that. Everybody see how that worked? So let's take stock real quick. I mean, I think this worked out really nicely. It's a lot better than trying to draw the cross sections, and again, the art on that is non-trivial. So, how did we get so lucky for this to work out? And I'm going to make a couple observations. First of all, the shadow. We need the shadow to be something that's nice looking, right? The fact that this looks nice is why this was not hard to do. We also needed for the lower bound to come from a well-defined single one of these given surfaces, and we needed for the upper bound point to come from a well-defined single one of those surfaces for this to work out reasonably. So that's what I have back here. That's what I mean by a good projection. You want to have a desirable shadow. What color did I use for that? I used the wrong color. You want a desirable shadow, and you want the top and bottom surfaces to be consistent and desirable. In other words, you don't want to put yourself into a situation where like that top surface is something where you can't solve for Z or something like that. Okay. I think this is one of the most important techniques for how to do triple integrals. I think it turns lots and lots and lots of really hard problems into much easier problems. I don't want to say always. It's an overstatement to say always. There are some examples of triple integrals where you do have to think about the slices. But man, surprisingly often, if you think about things in terms of project, think about the different options of how you might project. Very often it makes the problem turn pretty easy. So here's another example. Unit ball. Now the unit ball is hard to deal with. You can see this coming. Look at all the square roots. Can't help it yet. We're going to have, by the way, another really really cool way of dealing with the unit ball that'll come up later. But for the moment, rectangular coordinates, that unit ball, you can think about slicing it, let's say perpendicular to the x-axis. Those slices are surprisingly hard to draw without making it look sort of unrealistic somehow. And then you can talk about, okay, for one of those slices, if I slice perpendicular to the z-axis now, what do those look like? And then where do y start and end? And you can see these pictures get a little fussy sometimes. Again, so give it a try. I think you're going to find it's not falling down simple to draw these figures. It's doable. It's not easy. So here's my projection argument. I'm going to arbitrarily, no particular reason, say let's project to the xz plane. dz and dx on the outside. No particular reason, but let's just say. And so first of all, easy observation. If I want to project, if I want to look at just the x's and z's in the xz plane corresponding to points on this ball, it's pretty obviously a unit disk. The unit disk is pretty easy to draw. Let me just whip it out over here real quick. Unit disk, something like that. And of course, that's 1 and that's 1. By the way, this is on the xz plane because that's what we're looking at. That's where the unit disk is, where it came from. And how do you slice up this? Well, that's just kind of a double integral question and not even a particularly bad one. And boom, there you go. Two-dimensional picture. Two-dimensional pictures, we know how to slice those up, and these are the bounds that result. Notice I didn't have to fuss around very much with the three-dimensional picture. Just enough to be able to infer what the shadow looks like. Okay, that said, now what are my y bounds? Well, okay, so I'm going to have to sort of fix values of x and z. So I'm going to pick some point in that shadow. Some value of x and z. And I'm just going to think about, all right, well, Where is the starting value of y going to be? What surface is the starting value of y on? That hemisphere. Where is the ending value of y? It's going to be on that hemisphere. And I can write down the equations for those hemispheres pretty easily. Let me just go ahead and do that. We know the sphere overall is x squared plus y squared plus z squared equals 1. Solving for y, let's see here, let me do it like this. Y is plus or minus square root 1 minus x squared minus z squared. And which of these is the purple and which of these is, which of these is the orange and which one is the blue? Well, you look at the picture and I can see here from the picture the starting value for y clearly going to be a negative value of y. And so we pick negative, but whoopsie, we pick negative for the lower bound for y, and then likewise, pretty clear from the picture, that upper bound for y is going to be on the right hemisphere, which has positive values of y. And so that's the upper bound. What do you think? Everybody see the strategy there? And again, if you want to slice and then slice your slice, and then slice your slice of your slice, you can. It's just, I think it's harder to draw, and I think this projection argument's just a lot easier to work with. Okay. All right. Moving along. This is one of my favorite examples. It's a hard example. I'm going to start, before we start doing projections or slicing or anything of that sort, let's just start with how to draw this. The question is pretty hard as stated. If I give you that we're looking at 5 planes, in general, if I were to just say here's 5 random planes and ask you to identify what is the solid that's bounded by those 5 random planes, oh my gosh, super hard. I'd be scared of that myself. It's pretty non-trivial as a general situation. But we have a massive bit of good fortune here, and this is going to be a callback all the way back to chapter 1, section like really early chapter 1. We made this observation that if you have planes that don't have any y's in their equations, that means that they are parallel to the y-axis, and that really makes them a lot easier to draw. Right? Does everybody see how that happened? Right? So we got 3 planes here. You just happen to notice no y in 3 of the planes. It's a good thing to be on the lookout for. And knowing that they're parallel to the y-axis, I mean, within the xz plane, I mean, here's z equals 0, and here's z equals x, and here's x plus z equals 2. And so those planes are kind of, be kind of like this. Makes sort of a prism. Everybody with me? So we're 60% of the way done, and it was easy so far. So really nice trick. Now you do have to look at the others. Okay, so y equals 0. All right, well, sure. That's how y equals 0 intersects. Yeah. And the hard one, this is, oh man, it's just, this plane is, have to zoom out a little bit here. It's like it's something like this, and now you really do have to kind of use your 3-dimensional imagination. We've got this green prism, and this orange, it's like we're making an angled slice, right? It's sort of angled in all directions, right? There's no missing variables at all. Oh man. this is approximately what you get. Is this cross section right here? And if you really want to, I mean, if you feel like you need a little help in seeing, what this looks like, you are perfectly welcome, of course. Here, let me erase so I can highlight a different way. To think about, like 1 point at a time. Like, where's that point? You could literally solve for that point by noticing that it is on the plane x plus z equals 2, and it is on the plane z equals x, and it is on the plane x plus y plus z equals 3, and then you can straight up solve for x, y, and z, and that'll tell you exactly where that point. And if you wanted, if you just can't quite visualize everything, and if you have to actually do that to draw the picture, then yeah, cool. No problem. Okay. All right. Okay, so there's our picture. Now that we have the picture, slicing begins. And I think it's a healthy exercise. I think everyone should do the following. Go through all 6 slicing options. And what you're going to find is that only one of them is acceptable. So, for example, if you start slicing perpendicular to the y-axis, your slices look like that until you hit this corner, after which your slices look, qualitatively different. Because you slice through a corner and it's different faces that give the resulting edges. Everything's different. So that's a bad way to slice. You don't want to put dy on the outside. Everybody see what I'm talking about there? Okay, so again, unofficial suggested exercise. Think about all 6 options, and I think what you're going to find is that they all stink, except for one. The one that doesn't stink is this one. Okay, but now here's a different way to think about it, and I think this is really the better way to think about it, and that is think about projections. And I'm a big fan of this idea of the projection point of view. So let's play the game. What if I were to project, you know what, let me not, here I got a clean slate here. What if I were to project down into the XY plane, and I look at that projection and I say, you know what, that projection's not bad. It's a, what do you call it, trapezoid? Is that a trapezoid? I think it's a trapezoid. Not such a terrible thing. So tempting to think about that one, and then tempting further to say, well, look, the lower bound for z is always going to come from this plane, and that's easy. That's z equals 0. Here's the problem. The upper bound for z is sometimes going to come from that plane, and sometimes going to come, whoops, I wanted to change the color. Sometimes going to come from that plane, right? Imagine, if you pick a point in this purple projection, and if you start going up, well, oh my gosh, excuse me. Oh my God, and furthermore, sometimes it's going to come from that plane. We kind of have 3 different possible upper bound planes, and that's not consistent, and I'm not going to be able to make my projection argument very conveniently that way. So I'm going to call that a bad idea. This projection is not helpful. And you think about the other options, and you find that, again, only one works out well, and that is if you project into the XZ plane. And with the XZ projection, the lower bound is always on that one plane. Lower bound for Y, always on that one plane. And the upper bound for Y is always on that plane. And not so differently from the example on the previous page, that shadow gives me my z and x bounds, and solving for y on the green surface gives me my lower bound for y, and solving for y on this blue upper bound surface gives us our upper bound for y. Boom. Minimal extra 3-dimensional drawing. and no difficult algebra to be done. It's kind of fun. Everybody happy? All right. Okay, I think this is the last example. Okay, so last example. This timing's going to be just fine. So this is another weird one. We've got this. Okay, that's a paraboloid. By the way, flashbacks chapter 2, right? Everybody remember that you notice it's rotationally symmetric around the y-axis, and you think about the cross-sec, pick your favorite plane containing the y-axis, you do the rotation, make sure you're really good with all that stuff, right? So that gives us that, and now we've got this, also a paraboloid, again, chapter 2 flashback, blah, blah, and it ends up being this. And our actual solid here is what's bounded in between those. And it's weird and hard to draw because, it's tempting to say that it's this right here, but it's more than that. Because there's kind of like you think of the blue as sort of a bite being taken out of the sort of the center of this, what was inside the green. But there's still some solid that's kind of this side of the blue, and there's still some solid, on the far side of the blue. And if I color all of that in, now it looks like it's just a whole solid thing. It's a confusing thing to try to draw perfectly, and you just have to accept poor as about as good as you can do. All right, we're trying to understand a weird three-dimensional shape with a two-dimensional screen, and it does not work very well. Okay, so nevertheless, this is what we're going to have to work with. And again, you can try to draw cross sections, and man, this is a hard one. Here, let me try to draw a slice perpendicular to the z-axis here. Ooh, golly. I didn't do a good job on that. It's hard to do a good job, but that's, for example, poor art aside, approximately what a z-slice would look like. And then you think about how to slice that up. You can see the art challenge on this is going to be rough. Okay, so I don't want to do this in terms of slices because, man, that's hard. But on the other hand, look how easy it is to think about the projection, and the projection of this is clearly just a disk. Do a little algebra to find that, and the projection to the XZ plane. Since I put X and Z on the outside like that, projection to the XZ plane, boom, easy to do. It's just a disk. Slicing up a disk is no problem. It's just like a double integral. We're 2/3 of the way done. I am. Everybody happy? And then I just got to think about, okay, well, if I look at one of those slices, so for example, here is one of my slices in the y direction, and what do I get? Let's see, can I get all this on the screen? Anyway. I think we need to get it all on the screen. The starting value for y is going to come from that point, which is on that surface, which has an equation that we're given in which if you solve for y, you get this. Just given in the statement of the question that equation was y equals 2x squared plus z squared. And then the upper bound for y is at that point, which is on that surface, which again has an equation that we're given in which if you solve for y, you get y equals that. And so actually pretty easy to do this one, thinking about it from a projections point of view, whereas the slicing point of view would have had these artistic challenges that are, rough. By the way, for whatever it's worth, I do like the idea of challenges. right? Give yourself challenges. It's a good thing. It helps build mathematical muscles, and the more you try to draw difficult drawings, the better you will get at drawing. Please do watch those videos. I think they're really helpful. I think there's a lot of good little tips and tricks. You don't try to reinvent the wheel, right? Got videos that tell you how the wheel works. Use that, right? But still good to give yourself these artistic challenges. Just don't give yourself challenges unnecessarily on the exams, right? And so this is it'd be a good exercise to think about doing this with slices, but in practice, do it this way. Everybody good? Okay. Call it a day. See y'all later. Have a good one. See you tomorrow. Whoa.